Moving right along, we'll now turn to our famous dueling substituents segment. Well, I'm not so sure about the famous part, but anyhow, let's just kind of do a quick overview of where we've come from. Basically, started chapter 23 by giving you the whole big picture of how you predict, products based on the mechanism in regiochemistry and reactivity. So that's directing effects. And again, the reactivity we just saw. Now we're looking at different synthetic considerations. So finally we're at this dueling substituents. Life isn't usually very simple. And so naturally it makes sense that there's going to be times when there's two or more substituents on the aromatic ring. In which case I need to start thinking about, well, where am I going to be able to put my new substituent, my bromine or nitro group? Where is it going to show up? So, for example, looking at the methyl nitrile here, what do I have? What's going on? Well, I know that this methyl group is an electron donating group, and the nitrile is an electron withdrawing group. So that means this guy should direct meta, and this guy should generate orthopara, as neatly summarized in these two arrows. So the methyl group says go here. The nitrile group, oh, well, that's great. The nitrile group says go there as well. So when I do my electrophilic aromatic substitution reaction, yay, I only get one product. And there's no issue. So when the substituents reinforce one another, it's a happy day. Okay, what about this example? Now I have electron donating group. That's telling me orthopara. I have electron withdrawing group telling me meta. Ooh. So what should I expect? Well, the electron donating group, you recall, activates the ring. It's pushing electron density into the ring at these three blue arrow centers. So it stands to reason that those are going to be the fastest places to react, and I'm going to get this product, and this product. Definitely not in equal amounts. So let's assume we took a GC trace of this, and we got a little teeny peak, a gigantor peak, and a decent sized peak. Which one do you think is which? Which of these do you expect would be the minor product? Well, basically sterics and electronics cover just everything. So even though electronics is telling us we'll get all three of those products, really, this is pretty sterically hindered. So if we call these A, B, and C, I would definitely say this is B, a very minor product, because it's pretty tough to get your electrophile to go in between two substituents. Then we've got the para versus the ortho. I don't know. That's a crapshoot. I probably should have made the two peaks a little bit closer in amount, because they're both ortho to a substituent, so they might be formed in roughly equal amounts. But B, definitely a minor player. Beyond minor is the product that would be derived from meta direction by the sulfone here. That's not going to be formed because when the two substituents don't agree, it's that activating group that calls the shots. Okay, so here is a a list or a table of possibilities for you to think through. So go through that same exact practice that we just did on the previous slide to figure out, if I brominate this and it only brominates once, where would the mono-bromination product be? And maybe you'll see that you'll have more than one product, but definitely think through what the likely scenarios are. Alright, now let's say we want to start making some of these molecules that have more than one substituent, like, for example, this meta-bromoacetophenone. Now all of a sudden you have two choices. I can put the bromine group on last, this pathway, or I can put the ketone group on last, this pathway. So you got to think about the order of addition now, because sometimes only one will work. So for example, if I start with benzene and brominate it, no problem there, but now my benzene is an ortho-para director. If I go ahead and do Friedel-Crafts acylation on bromobenzene, I'm not going to get this product. I would get para-bromoacetophenone, which is not what I want. So that's not going to happen. So this guy, no good. Well, will this work? We know we can do the Friedel-Crafts. That makes acetophenone. Now, can I brominate? Will bromination with my regular bromination conditions give me this product? Yes, it will, because this is an electron withdrawing group and therefore a meta director. So this pathway is the pathway I must use to go from benzene to meta-bromoacetophenone. How about this example? All right. Now I don't have any problem with directing. Both this guy and the nitro group are meta directors, so you'd think, well, so what? It doesn't really matter, does it? Well, it does matter, because in the case of carrying out the Friedel-Crafts, we know that the Friedel-Crafts reaction will not work on a deactivated aromatic ring. So this pathway is a no-go. If I want to make this particular aromatic ketone, I have to take this pathway. So you see, synthesizing these substituted aromatics is both a fun little strategy game, but it can also be kind of tricky. And sometimes the tricks require using these temporary blocks. And I'm not going to go through, I'm going to go through these examples quite quickly because these are exactly the same examples as Cardy shows. Basically, the problem with this synthesis is twofold. Number one, we've already seen one, and that is the possibility for multiple bromination. So we don't want polybromination to take place. That would be bad. But we licked that by using acidic conditions. But let's say, we know we're going to get a fair amount of the para-bromophenol. And you know what? I don't want any of the para-bromophenol. I only want the ortho-bromophenol. So you can trick the system by blocking the para position with a temporary group, because we know we can take the sulfonyl group back off the aromatic ring later. The part about this example I don't really like is that you'll probably get a little bit of the ortho-sulfonation as well. Even though he says it really doesn't happen there, there'll be a trace. There'll be a trace. So it'll be kind of a pain in the butt. But you can do this and then brominate. And then that will give you this guy. And then, that's great, because it's meta to the sulfonyl, it's ortho to my ortho director, but then there's a whole nother step. I have to take the darn sulfonyl back off. So it's a typical, you can't win with protecting groups. You've got to add an extra step to put the protecting or the blocking agent in. You have another step to take the blocking agent back off. Kind of a drag. But you got to do what you got to do. The other example is this one, which is very clever. And that's basically that you can make, wow, how can you do this? This is an ortho para director. This is an ortho para director. How do you get them mated to one another? Well, the way you can get that to work is, well, check out the book. It's a very clever use of the nitro group, which can be converted to from a meta director to an ortho para director to the diazonium ion, which can be replaced with a hydrogen. So this really is a pain in the butt. My goodness, how many extra steps do we have here? But if that's what you have to do, shoot, that's what you have to do. All right, so that's it. And the last topic is basically other aromatics and nucleophilic aromatic substitution. But before you look at that next mini lecture, remember these wise words. Don't sweat the petty things, and don't pet the sweaty things. Ooh. And on that note, I will sign off.